Greetings. Welcome to another edition of our World Spaceflight News Space Newscast. SpaceX achieved another successful return of a Crew Dragon capsule from the International Space Station on Friday, marking the conclusion of the Crew-4 mission. Following several days of weather delays, the Freedom capsule gently splashed down on 4 good main parachutes off the coast of Jacksonville, Florida. The 4 crew members, Lindgren, Hines, Watkins, and Cristoforetti, were quickly retrieved by the SpaceX recovery vessel Megan, named after Crew-2 astronaut Megan McArthur. Here are the highlights.
Dragon, SpaceX on the big loop, all hooks open.
Copy. See the burns.
And Dragon separation confirmed.
Freedom on the big loop for hatch closure.
Go for hatch closure.
All 12 hooks now open.
As we were getting ready to close the hatch, Samantha just noticed that it looks like
Hooks all open and release confirmed at 11:05 a.m. Central Time, while Dragon and the International Space Station flew 259 statute miles above the North Atlantic Ocean.
Outer hatch seal.
Freedom Station on the big loop.
And Dragon concur with the action there, push the seal back into the groove and continue with hatch closure.
Safe re-entry and landing and calm seas. We're going to miss you guys. We're thankful for your mentorship. Enjoy your time with your families.
For the good work station, it was an absolute pleasure and privilege to be at station these past 6 months, and a joy to get to work with you all for the past couple of weeks. We know that you're going to continue to do amazing things on station. We look forward to seeing you back home as well.
And those were words from the crew on the ISS to the crew inside Dragon Freedom, giving them farewells as they head on their journey to back to home on Earth. You're looking live inside of Dragon
And Freedom SpaceX on the big
where they
loop,
currently have a
depart burn
go
0
for
was
hatch
nominal.
closure.
Copy.
We see NASA's Jessica Watkins and ESA astronaut Samantha Cristoforetti working to get the hatch closed. We're listening for that final confirmation for hatch
the
closure.
orbital outpost is complete following a 6-month science and research mission.
Once Dragon's hatch is closed,
Undocking occurred at 11:05 a.m. Central Time,
fix a docking
12:05
target
p.m.
outside
Eastern
of the
Time,
APES hatch
while the
on
International Space Station was flying
and
over
then
the
close
North
it,
Atlantic
creating a
Ocean.
space between Dragon and the station known as the vestibule. She'll then make her way out of the pressurized maiden adapter and close the forward hatch and close the zenith hatch on node 2.
And there's those drogue chutes, and you can hear the crowd here very excited to see them deploy.
Once all
Drogue
hatches
chute
are closed,
descent
a
rate
ground
nominal,
command
visual
will be
on 2 healthy
sent
drogues.
to open valves on Dragon to begin depressurizing the vestibule.
Freedom copies. We see that black and closed. So request manual override for detail 1.
Very cool view of Dragon with the 2 drogue
Standby
chutes.
1.
We are just
We are waiting to
anticipating
send the
the main
command
chutes
for
to
hatch
deploy
close,
here
standby
shortly.
1. Main chute, descent rate nominal, visual on 4 healthy mains.
And great news, as you can see there, the main chutes have deployed, slowing the Dragon vehicle down significantly, down to approximately 119 miles per hour.
Freedom is 1,000 meters.
Copy 1,000.
Now, Dragon has saved all propulsion systems and is now terminating the nitrox suit and cabin purges. and is beginning to increase.
800 meters.
Copy, 800.
Dragon is beginning to increase pressure in preparation for landing. And the mission control team here in Hawthorne is reporting the precise landing coordinates to the recovery team.
We copy.
So we did get that confirmation on the main chutes.
600.
The crew is now 600 meters away from splashing down. We do expect splashdown in about 2 minutes from now.
Landing in water is simpler, therefore more reliable, and it provides more margin against unlikely parachute.
400 meters.
Copy, 4.
Provides more margin against unlikely parachute issues. We had to learn how to make Dragon waterproof, but once you do, it is a rinse, review, and reuse type of process. And we are just about a minute away from splashdown of the Dragon vehicle back onto planet Earth, and hearing good callouts of the altitude of Dragon.
As at 200 meters, we're bracing for splashdown.
Copy, brace for splashdown.
And again, that descent rate is as expected here. Pretty soon we should be able to see the view of the ocean come into view as Crew Dragon Freedom with 4 astronauts on board prepares to splash down after spending 170 days in space after launching on April 27th.
HL, just keeping you in the loop. Ground teams are looking through reconfigurations after we sent that hatch close command. We are going to perform a small pressure bump here. You'll see, you might notice some gas injections here shortly as we raise the cabin pressure closer to our free flight boundaries.
The crowd goes wild for Crew-4.
Copy, Freedom, SpaceX 3 splashdown and mains cut.
Welcome home. Welcome home, Crew-4. Great view watching Dragon splash down back on planet Earth.
A magnificent sight in Boca Chica as a fully stacked Super Heavy booster and Starship were united on the Starbase orbital launch mount this week. Further cryogenic and engine testing is expected prior to a launch attempt for the Mammoth, groundbreaking rocket. In a dramatic announcement headlined by NASA Administrator Bill Nelson on Tuesday, it was confirmed that the DART asteroid mission was a truly historic success. The kinetic impact successfully altered the asteroid's orbit, marking humanity's first intentional change of the motion of a celestial body. Before its encounter, NASA had defined a minimum successful orbit period change of dimorphos as a change of 73 seconds or more. This early data show DART surpassed this minimum benchmark by more than 25 times. Here are the highlights of the press briefing.
And so today, NASA confirms that DART successfully changed the targeted asteroid's trajectory. Now, how do we know that? Well, prior to DART's impact, it took Dimorphos 11 hours and 55 minutes to orbit its larger parent asteroid, Didymos. Since DART's impact, astronomers have been using telescopes on Earth to measure how much that time has changed. And now the team has confirmed that the spacecraft's impact altered Dimorphos' orbit around Didymos by 32 minutes, and therefore successfully moved its trajectory. In other words, DART shortened the 11-hour and 55-minute orbit to 11 hours and 23 minutes, and it moved it in another location. And that has been confirmed by the telescopes.
Just to give an idea, we're talking about monitoring an event while traveling at a relative speed with respect to the asteroid of 6 kilometers per second, about 4 miles per second. So the LICIA had to watch the event and then do a flyby of the two asteroids and turn to continue monitoring what was happening. It was really something challenging, but when after the impact took place, you can see we have prepared two videos. The first one shows the last seconds before the impact, and you can see the change, basically a little change in the little dot, which is Dimorphos, showing the ejection of the material. But of course, a second video we prepared shows what actually happened during this approaching of Dimorphos, the flyby and the turning of the satellite, and getting far away. So what you can see in the second video is actually the approaching from 700 kilometers of distance, then the flybys where we went very close, up to 59 kilometers from Dimorphos, and then you can see while we're getting more far away of about 300 kilometers. So I believe what you're seeing here is really fantastic. I remember the night when from the control center at the Argotech premises, our prime contractor, we started looking at those images. We couldn't believe our eyes that actually we made it. And we made it thanks to this fantastic collaboration with colleagues from NASA, and we are really proud of that.
We've had observations from around the world, ground-based telescopes and even a couple space-based telescopes. I just want to share a couple of them with you here. This image here was taken by the SOAR telescope in southern Chile. And let me just describe a little bit of what you're seeing. You just saw images from the Lucia cube going head on, looking at a cone of ejecta coming off of Dimorphos. Well, here now you're looking at an image, that same kind of view, but from side on. So you're seeing that ejecta cone kind of facing out to the left. And you can see one arm of that cone pointing down to about 8 o'clock, and then the top arm of that cone pointing up to about noon. And so we can see that cone here from the ground. You also see this really bright streak going off towards about 2 o'clock. And it looks kind of like the tail of a comet. And that's because what we're seeing there is this fine-grained particles that were ejected from the asteroid being driven away from the asteroid by solar radiation pressure, very much akin to a comet. So very cool observations here. This image was actually taken 2 days after the impact. And if we go on to the next image, please. We're continuing to take images. This is the latest and greatest, hot off the press, Hubble Space Telescope image that was collected on Saturday. And what you can see here is that ejection cone, again, we're looking side on, that bottom arm of the cone is still pointing down to about 8 o'clock, but the top part of that ejection cone has kind of gotten pressed back, again, with that solar radiation pressure. And you can also see that comet-like tail has now kind of split into two as it gets away from the asteroid. This is so fresh and such a new image that the scientists are still working on interpretation of that kind of double bifurcated tail.
So digging into the data, one thing I want to stress up here at front is that there are two different types of observational data sets, both completely independent, that were used from data collected here on the Earth in order to arrive at this result of 32 minutes for the orbital period change. And they're both completely consistent and supporting this result that we've heard, of this 32-minute orbital period change. If I could have the first animation, please. The first data set and method used by the DART team uses optical telescopes here on the Earth. And so these optical telescopes here on the Earth can never actually tell the difference between Didymos and Dimorphos. As it looks to these telescopes, this asteroid system is always just a single point of light. But that single point of light changes in brightness with time, as seen by these telescopes, because sometimes the little asteroid Dimorphos passes in front of the larger asteroid Didymos, and there's a little bit of a shadow. But then other times it actually passes right into Didymos' shadow. This is a Dimorphos eclipse. And so you can see from these eclipse events that the telescopes see a decrease in the overall brightness of this asteroid system every time that this happens. And then you can also see that these eclipse timings are very much related to the orbital period of Didymos around Dimorphos. So by measuring when these eclipses happen, you can determine what that orbital period is. And I also want to take a moment here to say the DART team already did this. We did this in order to get the timing for DART's kinetic impact event. So when the DART spacecraft was speeding in to hit Dimorphos, it was really important that Dimorphos wasn't hiding behind Didymos or located in front of Didymos at that time, but was actually off to the side. And telescopes on the Earth, the DART team had used those data in order to get that timing to inform when the DART spacecraft should show up so that the autonomous navigation system could separate Didymos from Dimorphos and target onto Dimorphos and squarely hit it. And we see that that positional information that the team had was excellent, and Dimorphos was exactly where it was expected from the analysis of this telescopic data. So this is just to say that the team was highly experienced and practiced at already using this method of telescopes to understand where Dimorphos is relative to Didymos. If I can have the next graphic, please. So ever since the event on September 26th, 2 weeks ago, these telescopes have been observing this system nightly. And that's what you see going across here on this graph on the top. Just this nightly telescopic data, night after night after night after night, all added up there. There's actually 4 different telescopes on the Earth that have contributed to making this graph so far that you're looking at in this result that we're presenting today. It's the Las Campanas Observatory in Chile, the Las Cumbres Observatory Global Telescope Network with facilities both in South Africa and in Chile, and the Danish Telescope in Chile. And all 4 of their data have excellent agreement and are all just overlaying on top of each other right here. Additionally, the DART team has 2 independent research groups that have looked at analyzing this data separately, and they have come to exactly the same conclusion. So this is also then showing 2 examples of this much larger data set blown up so you can see the actual data on September 29th and on October 4th. And what you see very clearly in that data is these dips in brightness that we were just talking about with that animation. And these dips in brightness were confirmed by these 2 independent research groups, and they are consistent and indicate that the orbital period of Dimorphos around Didymos currently is 11 hours and 23 minutes. What you can also see here is that it is not consistent with being 11 hours and 55 minutes as it was prior to DART's impact event. And this is very strong, conclusive evidence the team is very confident in of this 32-minute orbital period change. Now, the second data set that was used independently is planetary radar. And the planetary radar facilities used were the Goldstone Observatory in California and the Green Bank Observatory in West Virginia. What's nice about planetary radar is that in contrast to the optical telescopes, you can actually distinctly get signal from both Dimorphos and Didymos directly. And this is an important distinction. So the Goldstone Observatory in particular has been tracking the position of Dimorphos regularly every night for the last 2 weeks, roughly. And from those, they have also been tracking that this is an 11-hour and 23-minute period currently for Dimorphos around Didymos with a 32-minute orbital period change. If I can have the last graphic for me, please, here. Additionally, on October 4th and October 9th, these radar facilities were able to get some direct images of the Didymos and Dimorphos system. Here you see Didymos, but also directly in the image, you can also get signal from Dimorphos. And so we're directly imaging both of these asteroids and getting their positions relative to each other. And the position of Dimorphos is consistent with 11 hours and 23 minutes for its orbital period, and it is not consistent with being what the orbital period was prior to the DART impact, which was 11 hours and 55 minutes. And so this is just another example of these 2 independent methods all giving you this same answer. So this is a very exciting and promising result for planetary defense to have this orbital period change of 32 minutes. It's within the range of the models that have been studied, but it's also definitely indicating that you're getting an enhanced deflection due to the amount of ejecta, that rocky material that's being thrown off when DART's collision happened. I think it's also, though, important to put this into perspective of a kinetic impactor technique if you wanted to use this in the future, potentially to deflect an asteroid. This is a 4% change in the orbital period of Dimorphos around Didymos. And it just gave it a small nudge. But if you wanted to do this in the future, potentially, it could potentially work, but you'd want to do it years in advance. Warning time is really key here in order to enable this sort of asteroid deflection to potentially be used in the future and is part of a much larger planetary defense strategy.
It looks like the recoil from the ejecta blasted off the surface was a substantial contributor to the overall push given to the asteroid, in addition to the push of the spacecraft directly impacting. And this is a spectacular image taken from LiCi and enhanced by the DART team to bring out fine structures. The rectangles that you're seeing are not real. It's just that in each successive rectangle, the contrast has been boosted by another factor of 2 in order to bring out that faint structure. And this is just a visually stunning image. And every little wiggle in those streamers, every little blob, every little particle that you see is a clue to something. It's a clue to something that happens on the surface of an asteroid when an object impacts it. And if you're looking at this image and a dozen new questions are popping into your head that you would have never have thought to ask before seeing this, well, that's just one of the hallmarks of great science. It opens up new questions that we would have never have thought to ask. But in addition to the science value of this image, I really love it because it is artistic, it is poetic. The team before Impact has been spending years trying to understand the range of possible outcomes of this experiment, not knowing what the target was going to be. And so they did simulations on solid rocks and broken rocks and fractured rocks and piles of rocks and rubble piles and piles of gravel. And there was this immense range. And one of the things we did understand from those simulations is that we expected a solid rock to be less responsive than a pile of gravel. A loosely bound rubble pile would have a big response. So I won't speak for anybody on the team other than myself, but the last few minutes before impact on the 26th were quite dramatic. And when I saw Dimorphos come into view, and when I saw there was not a single crater on it, and there were a lot of what appeared to be loose rocks, and this was a totally non-scientific by-eye measurement, I looked at it and I said, this is not going to be 73 seconds. And it wasn't.
So the observational campaign for the DART team will continue. The timing of DART's impact into Dimorphos was actually chosen when the distance between Earth and this asteroid system is at a relative minimum. And so observations can actually continue into early 2023. So right now we have this orbital period change of 32 minutes with an uncertainty of plus or minus 2 minutes. Additional observations will help to better refine that answer. In addition, the tail is spectacular, this amount of ejecta that you're seeing, and it's continually evolving. And so the observations are going on in order to fully track and watch that evolution of the ejecta. And so these are the two main things that the observations will continue to be doing for the weeks and months to come.
On Saturday at 1:22 a.m. Eastern, Falcon 9 launched the Eutelsat Hotbird 13F mission to a geosynchronous transfer orbit from SLC-40 at Cape Canaveral Space Force Station in Florida. This was the third launch and landing of this booster, which previously supported the launch of CRS-24 and one Starlink mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power and ignition. Lift off of Falcon 9. Go Hotbird, go Falcon. Vehicle is pitching downrange.
Falcon 9 has successfully lifted off from Pad 40 at Cape Canaveral Space Force Station, carrying the Eutelsat Hotbird 13F satellite. During ascent, the M1D engines will actually swivel and help steer Falcon 9. This is known as gimbal. The rocket autonomously tilts the engines just a few degrees, and the
Falcon 9
skimbling
is supersonic.
allows the vehicle to perform a gravity turn, which is when we go vertical as well as horizontal. So we're still going up, but now we're also heading horizontally away from the launch pad.
Max Q.
And there we heard the call out for maximum aerodynamic pressure. So now we'll throttle those 9 M1D engines back up. In about a minute, we'll have 3 events occurring in quick succession. The first will be main engine cutoff, or MECO, as it's seen there on the timeline at the bottom of your screen. MECO will be followed immediately by stage separation, which, as the name indicates, the first stage and second stage will separate. And then the second engine, that Merlin vacuum engine, will ignite for SES-1, or second engine start 1. Everything continues to look nominal for the first stage. It's a great view of the M1D exhaust plume. Standing by for main engine cutoff.
MECO. Stage separation confirmed.
And there you can see that MVAC has ignited, that nozzle turning orange and white. Those 3 events happening rapidly. The first stage there on the left-hand side of your screen, and the right-hand side for the second stage.
Both vehicles are following nominal trajectories.
Next major event is fairing separation, occurring in about 10 seconds. We can see the Space Coast in the distance background of the left-hand side of the screen.
Fairing separation confirmed.
And there's our first look at the Eutelsat Hotbird 13F payload. Now, those fairing halves that we just separated, we will be attempting to retrieve them again once they fall back to planet.
MVAC shutdown.
All right, we started to see that the MVAC nozzle was losing that bright white glow, indicating we had a second engine cutoff. And there on the left-hand side of your screen, you can see that the first stage has begun the landing burn.
Nominal parking orbit.
Heard good orbital insertion there for the second stage.
Stage 1 landing leg deploy. Stage 1 landing confirmed.
And there you have it. That landing marks SpaceX's 147th recovery of an orbital class rocket, including first stage landings for Falcon 9 and Falcon Heavy. Now, as far as the mission, we had an on-time liftoff at 1:22 a.m. Eastern Time, followed by successful ascent, stage separation, first stage landing, and 2 second stage engine burns. As a reminder, Eutelsat is a world-leading satellite operator in a footprint covering Europe, Africa, the Middle East, Asia, and the Americas.
Payload separation confirmed.
And there you see it on your screen. Payload separation confirmed for the Hotbird 13F payload.